In laboratory physics, researchers can directly manipulate variables to test their hypotheses. Astronomy, however, relies entirely on observing light and particles from a distance. To distinguish a robust astrophysical theory from speculative guesswork, researchers subject their ideas to a strict filter of falsifiability. Over the past century, several radical frameworks have emerged, claiming to rewrite our understanding of the cosmos. Two of the most prominent are the static universe, which relies on a mechanism called tired light, and the electric sun hypothesis. Proponents of these alternatives often rely on an actualistic methodology. The actualistic approach is a method of theoretical reasoning that takes observable laboratory phenomena and scales them up directly to explain cosmic structures. Standard astrophysics operates differently. It relies on predictive discipline, requiring models to mathematically anticipate observations before those observations are actually made by instruments. To survive, a standard model must reconcile with the convergence of independent datasets. Theories are evaluated exclusively through predictive inference against data gathered by high-precision satellite telemetry. This rigorous testing process acts as a falsification gauntlet. A theoretical model is forced to survive multiple overlapping physical observations that cannot be explained away by a single anomaly. The boundary separating accepted astrophysical models from alternative frameworks is not bias, but this strict requirement of predictive falsifiability across vastly different physical regimes. In 1929, astronomer Fritz Zwicky proposed the tired light hypothesis as a static universe alternative to the theory of cosmic expansion. The core mechanism of tired light assumes that photons slowly lose energy over vast distances by colliding with matter or other particles in a stationary universe, causing their wavelengths to stretch into the red end of the spectrum. This chart plots the tired light model's fundamental mathematical prediction, an exponential drop in a photon's energy over distance. The lambda CDM model provides a starkly different mechanism, where the expansion of space itself stretches the photon's wavelength in transit. While the mathematics of tired light offer an elegant alternative, any physical scattering mechanism that drains energy from photons must trigger secondary, observable phenomena. Because it requires physical collisions, the tired light model leaves itself vulnerable to independent observational filters, testing the behavior of light over billions of light years. The first filter is image blurring. If photons physically scatter off intergalactic particles to lose energy, their trajectories must deflect, disrupting the clarity of the image we receive on Earth. High-resolution deep space imaging shows absolute clarity. The sharp boundaries of the most distant galaxies show no evidence of scattering-induced blurring, directly contradicting the physical collision requirement. The second filter is the Tolman surface brightness test. This cosmological metric compares how the apparent surface luminosity of galaxies diminishes relative to their redshift. This data plot traces the static universe prediction. A stationary universe scales surface brightness on a shallow curve, but the expanding universe dictates a much steeper curve. Actual observational data points from galaxy surveys lock precisely onto this steeper expansion curve. The static universe model lacks the geometric mechanics to account for the specific, accelerated way galaxies dim over cosmic distances. The third filter relies on cosmological time dilation, utilizing the predictable fading cycle of distant supernovae as standard cosmic clocks. This is a relativistic effect, where events in the distant universe appear to occur more slowly because the expansion of space stretches the light signals reaching us. Under static universe logic, light loses energy, but distance remains constant. Therefore, a supernova exploding 5 billion light-years away should fade at the exact same rate as a local one. This visual compares supernova luminosity over time. The expanding universe model predicts spatial expansion will stretch the incoming light curve, making distant explosions unfold in slow motion. High redshift supernova observations precisely match this stretched temporal signature. The stretched duration of these light curves provides independent confirmation of spatial expansion. Static models relying purely on energy loss cannot replicate this temporal stretching. Moving from intergalactic space to our local star, we encounter the electric sun hypothesis. This alternative framework challenges the standard models of stellar physics. This hypothesis claims the Sun acts as a giant anode, collecting electrical currents from the surrounding galaxy. Proponents point to the solar corona, arguing standard physics cannot explain how the outer atmosphere reaches millions of degrees while its surface remains cooler. The standard solar model posits a completely different engine. It relies on a core of thermonuclear fusion, surrounded by distinct internal layers of varying pressure and density that transport energy outward. To resolve this debate between external electrical currents and internal nuclear fusion, physicists must measure the internal mechanical and thermodynamic structure of the star itself. We examine the interior using helioseismology, the study of acoustic pressure waves propagating through the Sun. By tracking surface vibrations, scientists deduce internal conditions. The specific speeds and refraction angles of these patterns map precise density gradients deep inside the star. These acoustic maps align directly with density conditions mathematically required to sustain core thermonuclear fusion. Crucially, this internal density gradient leaves no room for the uniform isothermal interior demanded by the electrical anode model. As for the superheated corona, standard plasma physics resolves the temperature difference through mechanisms like alpha wave reflection and magnetic reconnection. An alpha wave is a traveling oscillation of ions and magnetic fields, violently releasing stored magnetic energy when lines snap and reconnect. Modern spacecraft, such as the Parker Solar Probe, have flown directly through the corona and verified these magnetic particle interactions with in-situ telemetry. Internal acoustic mapping confirms a fusion-driven density gradient, while direct telemetry confirms magnetic coronal heating. Together, these measurements independently falsify the core claims of the electric sun model. Alternative theoretical models often gain traction by selectively highlighting specific, isolated anomalies while ignoring the vast, intersecting datasets that actually define the universe. The tired light hypothesis remains mathematically elegant only if one ignores the clarity of deep space images, the specific geometry of surface brightness dimming, and the stretched timelines of distant supernovae. The electric universe remains plausible only if one ignores the acoustic mapping of the Sun's interior and the direct magnetic telemetry gathered from its atmosphere. Standard astrophysical models are not arbitrary agreements among scientists. They are the specific frameworks left standing after passing through the gauntlet of physical observation. Modern astrophysics relies on the continuous testing of theoretical models against relentless, multi-messenger empirical data. Scientific validity is established not through scaled-up laboratory analogies alone, but through the survival of models under the strict compounding weight of observational reality.